Hello everyone, we're going to take a look at intersection of planes in this video. Planes can be thought of as surfaces, and how they intersect can be used in multiple different applications, but we're just going to be taking a look at the very basic mathematics behind calculations with regards to these and scalar equations of planes and how to work with them algebraically to determine certain types of intersection. So as you can see at the moment, we're just going to take a look at intersecting two planes because you can get more complex between 3, 4, 5, and so on. We're going to take a look at just the situation with 3 planes in a moment, but with 2 planes. So the idea with this intersection is if you are not told what kind of intersection you have, then you need to determine that before proceeding with any of the techniques. Okay. So how do you do that? Well, that is the big question. So we're going to take a look at some of those little samples, but the key pieces of information that can help you, especially when you're dealing with scalar equations of planes, are your normals. So should be relatively obvious. Let's just focus on case 2 and 3 for a moment. I'll come back to case 1. So if the two planes are what we call coincidental, all right, now coincidental means they're essentially one on top of the other. So there should be an infinite number of solutions. Now, when we talk about intersection, think of intersecting lines in very basic elements of mathematics. So lines can either be parallel, which means they do not intersect in two-dimensional space, or they can intersect in a point, or one can overlap the other, which means an infinite number. So the same sort of idea is happening here. You have one plane intersecting the other plane because they are coincidental. So there's an infinite number of solutions. Whereas you can have in case 3, planes being parallel and completely separate. So there are no points of intersection, right? Now your normal vectors here that are drawn will help determine this algebraically and logically in just a moment. Now, if the planes are not coincidental, they're not parallel, and that means they must be at some angle to each other, which means eventually they will cross in a line. So, and again, why is it a line? Well, it's going to go on forever because the planes go on forever. So you can see that line of intersection right in here. So you'd have to find the equation of that line. So that makes things a little bit more interesting when you're trying to find intersection of two planes. Okay. So steps for success. All right, so you can be given equations of planes in scalar format. This is where the normals are very important. So if the normals, you notice here, pointing in the same direction. So they are, what's the term for it? Collinear, yes. All right, or parallel. All right, it's another way of thinking of it. So in both of these situations, case 2 and 3, the normals are both parallel and collinear. So how do you distinguish between these two? Well, we're going to take a look at that in a moment. So if they are parallel, then you're looking at this possibility, either distinct or coincidental. How do we check? Well, from a scalar point of view, it should be pretty easy. The scalar equations, the coefficients will all be scalar multiples of one another. Okay, so that should be a pretty easy way of determining if the planes are distinct or coincidental. All right, so if they're scalar multiples of each other, then they're the planes would be coincident, otherwise they'll be distinct. Right? If the planes are not parallel and they intersect in a line, well, this is where you have to find the equation of the line. Now, the equation of the line is going to be based on more than likely the parametric equation. So we'll go through an example of that. But this is the process here to eliminate 2 of the variables and then rewrite using the third variable all of a sudden becomes a parameter. So let's take a look at an example of that. So I've got one set up for you here. And this one will do a couple of things. So notice it says find the intersection of the following planes. So you don't know that they're going to intersect in a line, but I've set this one up so that we can focus on that. All right. Now, the little symbols here, sometimes this is used to denote planes. So that's plane 1 and plane 2. Don't think of that as like 3.14 subscript 1. Okay, that's just a different way of identifying a plane. All right, so that's just fancy notation. So to determine the intersection of two planes, so you have to determine if these planes do intersect in any way. So are they parallel? Well, that means you're going to look at scalar multiplication of the coefficients. Now, to compare the coefficients rather quickly, you can do a little calculation. But again, we're focusing on the normals as well. So if the normals are scalar multiples, then the planes will be parallel. So that's what this is asking. And you can set up some quick little ratios to determine if that's true or not. Since it's false, then the planes are not parallel. If you know they're not parallel, then there's no way they can be either distinct or coincidental. So the only thing left is they must intersect in a line. So being organized and maybe having a little reference diagram if you really need it is going to be helpful. So the algebraic process to use these two scalar equations here to find that equation is this. So you pick any two of the variables that you want, x and y, x and z, whatever. And what you need to do is eliminate them using exactly that, elimination from like the grade 10 program to eliminate variables from your equation. So if we're going to eliminate x, I have a coefficient of 4, so I want to make sure I have a coefficient of 4 in the other equation. And since the coefficient currently is a 1, I'm going to multiply everything in that second equation or of the plane by 4. And then I'm going to subtract. So this is just doing an elimination process like you would back in the grade 10 program. And you come up with an equation. Now, the idea is also to solve for one of the variables, leaving the other one on the other side. And you're going to repeat the same process, but now you're going to eliminate a different variable. Okay? So here we wound up with eliminating x, so we have an equation with y and z. So we solve for y, leaving z alone. So when we eliminate y, we're going to get an equation with x and z. So that will make z the consistent remaining variable. Let's see how that works. So again, same sort of process. We're going to get another equation with x, okay, and z. So notice we solve for the two unique variables, leaving the non-unique variable on the other side. Now, what does that allow us to do? That allows us to kind of pretend that z is now our parameter. Remember parameters for equations of lines, right? Like in parametric equations. So if we let z become our parameter, we can now write parametric equations using this, this, and this. So take a look. So parametric equations have an x equals, a y equals, and a z equals. So the line that we're looking for, whoops, sorry about that. The line that we're looking for has 3 parametric equations, all right? So we can write it in parametric form. It doesn't really require any particular format. If you wanted to write it in vectored form, that's how it would be written. And that's about it. Okay, so this is a line of intersection, and we have to find that line of intersection. So simply to say that it intersects in the line is not good enough. You actually have to find that type of intersection. So we did find the line of intersection. Okay, so where things get a lot more interesting is intersection of 3 planes. So as you can see, the normal vectors are going to be very important again. So the coincidental and the parallelism is still going to be very important, but there's a lot more situations now to deal with. So you can have 3 planes that are completely separated and parallel. 2 of them might be coincidental, like here, and 1 of them might not. So you get parallelism, but 2 are coincidental. And then you can have all 3 of them are coincidental. And this is only one situation. We haven't even looked at some of the other ones just yet. Okay, so in the first case, there's no intersection whatsoever. So we say there's no solution. Here, there's also no solution because we're looking at how do all 3 intersect. Okay, we don't care about the fact 2 of them are coincidental. It's a combination of all 3. Is there intersection between all 3? And the answer is no. This last one here, is there intersection between all 3? Yes, because they're coincidental. And your solution is a plane or an infinite number of solutions, whichever way you want to look at that. Okay, so if you have a situation where the 2 of the normals are collinear, so let's take a look at this situation. So you have 2 of the normals here. Maybe we'll draw in a couple of normals. So one there and one there. Doesn't really matter the length. But so 2 of these normals are collinear. These 2 normals are collinear, but the third one is not. All right. So this third one again is not collinear. Might not be perfectly 90 degrees, but I'm sure you get the idea anyway. Okay, so perfectly drawn that way. So in the first situation here, again, is there intersection between all three? Well, yes, but it has to be the same intersection. So there may be a line here and a line here, but those are two different lines. So there's no singular intersection between all three. So we say there's no solution in this particular case where two planes are parallel and distinct. In this situation where two of the planes are coincidental and the one is not parallel to it, then there is a line of intersection. Okay, so the solution is a line, much like in the 2D case, or sorry, in the two-plane case. Okay, so how do you determine all of this? Well, we're going to take a look at that. We have a bunch of examples to get through. It's just a matter of trying to get the visualization here. And the last situation is normals are coplanar. Now, what does that mean? Well, that means that the normals that are created for each of the planes actually create a plane. Okay, and remember we talked about this, how do they create a plane? Well, they create a plane if you have these three types of directions, right? So they lie on a plane. Now, the one thing you got to keep in mind is if the normals are coplanar, there is no solution. Again, even though there's intersection between the planes, they are different lines of intersection. They must be all the same, much like in this case here. All right, so the normals are coplanar, but the solution is a line. So that's a little bit trickier. So you have the same language, normals are coplanar, but you can either have no solution or solution is a line, and we'll see how that plays out eventually. All right. Okay, so we'll take a look at that in a moment. And the fourth case is the normals are not coplanar and they are not collinear. So in this particular instance, they're non-collinear, but they're also not coplanar. All right, so what's going to happen there is you're going to get this kind of situation. So you'll have two of the normal vectors that are sitting on a plane, and then the third one's coming up at a 90 degree pretty much to both of them. You can think of it that way. And that is not coplanar. Okay, so coplanar, so all three of these would be on the same plane. Non-coplanar, the three different normal vectors would not be on the same plane. And what happens there is you get a unique point of intersection. All right. And some interesting language that comes along with this. So a system of three planes is either inconsistent if there's no solution, or it's consistent if it has one or more solutions. So one solution could be a point, more solutions could be a line or plane. Okay, so a lot of different language here. So we're going to run through some examples. And these are some steps for success in terms of working with this. So if you have the normals are collinear, then the solution is a plane or doesn't exist. So that's case one that I described earlier. If two of them are collinear, the solution is a line or doesn't exist. Again, that's case two. If they're non-collinear normals, then the way you determine that to see if the normals are coplanar, solution is a line or doesn't exist, is this kind of situation. Now, the triple scalar product is used to find the volume of a parallelepiped. So if volume of a parallelepiped, which is basically a fancy way of saying a box in three-dimensional space that can be slanted edges, if the volume is 0 and your triple scalar product is 0, then the solution is a line or it doesn't exist. And that's case 3 that we looked at because the normals are non-collinear. If the normals are not coplanar, the solution is a point of intersection. So that means the volume of the parallelepiped is not equal to 0. Okay, so again, we're taking a look at the volume of the parallelepiped using the normal vectors. Okay, so this will basically tell us that they're not coplanar because we don't get a volume. If you don't get a volume, then you can safely say the normals are coplanar. If you do get a volume, then the normal between the normal vectors using this calculation, then the normals are not coplanar and the solution has to be a point of intersection. Now, where you can save some time with a lot of the work that you will see, because we're going to take a look at some sample problems, is if you are told what type of intersection you already have. If you are told what type of intersection you have, then you can avoid certain calculations. You don't have to prove whether whether the normals are coplanar. You can just jump into solving. So you also have to take a look at what kind of information you're given and what kind of information you're not given. So with these sample problems, you have to determine the possible solutions. So you don't know what the solutions are to each one of these. Okay, so I'm going to run through one of the examples, a couple of them, in this video, and then I'm going to create a shorter video that links with the remaining ones if you wish to see that even further, to see how you would approach the situation if you're told what the information is and what you're not told what it is. Okay, so sample problem number 1 we're going to take a look at is part A. Okay, now part A, you always start with the normals. So you're trying to determine the intersection with these 3 planes. So you know you have 3 planes, you get 3 scalar equations. All right, determine which of the following systems contain parallel planes, coplanars, and state the possible solution. Now that language can change. That could just basically say, find the intersection of the planes. Okay, so you have to start off by examining the normals because you need to know what case are you dealing with. All right, so are the normals coplanar? Are they not? Are they collinear? What's going on with the different types of systems? All right, so you must compare the normals. All right, not a bad idea to label the planes as well. So, and the reason why we have to compare the normals is because we don't know what kind of intersection we have. I'll come back to if you do have the type of intersection, what you can avoid that. So if we take a look at the different normal vectors and we compare to see if they're scalar multiples. So we always start with this because we want to know if the planes are parallel. So we want to do this in pairs as well. So we take a look at the normal vector for plane 1 and 2. They are scalar multiple, which tells us that plane 1 and plane 2 are parallel to one another. However, let's take a look at plane 3. Now, plane 3 is a scalar multiple of, or the normal vector for plane 3 is a scalar multiple of the normal vector for 1. So plane 3 and plane 1 are parallel. So if plane 2 is parallel to plane 1 and plane 1 is parallel to plane 3, then all 3 planes have to be parallel. So if they're all parallel, think of this as 3 pieces of paper. Well, 2 of them can be one on top of the other, and then the other one distinct. All 3 of them can be together, or they could all be distinct. So that was that other situation I diagrammed out. So now it's a matter of, well, how do you determine what the situation is here, whether they're distinct or not? So you have to check for coincidence. How do you do that? Well, the easiest thing to do is to take a look at these values. Now you might be saying, well, what about the rest of them? The normal vectors came from the coefficients of the x, y, and z. So you've already worked with that to say that they are scalar multiples. So now we're looking at, are the values on the end, the d values. Remember, this is ax plus by plus c, z plus d. So are the d values scalar multiples? That'll tell us about coincidental. So we compare in pairs again. So, but the key thing is, why are we comparing it here with a 2? Well, if we take a look earlier, the normal vectors were scalar multiples by 2 for plane 1 and 2. So we're going to check the same thing, because if that's true, then they must be coincidental. So this is not true for plane 1 and plane 2. So plane 1 and 2, these ones here, cannot be coincidental because the scalar factor does not work for D. All right. So plane 1 and plane 2 are distinct. So you have one sheet of paper, another sheet of paper. Those are definitely, they're parallel, but they're separate. All right. And then you go and compare 1 and 3, much like we did before. So again, here we determined that the normal vectors had a scalar multiplication by a factor of 3. So we use the same scalar factor here. And this is true. So that tells us that planes 1 and 3 are coincidental. So plane 1 and 3 are exactly the same, but plane 2 is not, yet they're parallel. So is there an overall intersection? No, so there's no solution, right? So there's no interaction or intersection of the planes, okay? All right, now to take a look at this coincidental business. So this is a situation where if you're told that these planes do not intersect in a particular way, you can jump right into the scalar multiplications of the d values. So you may be told sometimes that two of these planes are distinct and the other one isn't. Well, then you can go through some proof. So all of this work is just basically proof as to the statements that you're given in certain questions. All right, so how much work you need to show really depends on the information that you're given and you're starting with. All right, so let's take a look at another example here. So in B, again, here we're comparing those. We're going to run through exactly the same process. It's a repeat process all over again. So we're going to go through comparison of plane 1 and plane 2, looking at the normal vectors, slightly different way of looking at it. So using ratios here. So these ratios are not all equivalent. So what can we say? Then the normal vectors are not scalar multiples. So plane 1 and plane 2 are not parallel. So we have one plane going this way and another one going that way. Now, there is a third plane, so we have to see what's happening. Is the third plane doing this, or is it crossing through the exact same point, which might lead us to some type of intersection? So we do the same thing with 1 and 3. So plane 1 and plane 3 are not parallel. So what does that tell us about all three of them? Well, not much yet. So we know that plane 1 and plane 2 do that. But plane 1 and plane 3 are also not parallel. So we need to double check to see what happens with 2 and 3. So or maybe 2 and 3 are parallel. And they are not. Okay, so if they're not parallel, so none of them are parallel. So no two planes are parallel. So we have one going that way, one going this way, and one going that way. Now the question is, do they all intersect in such a way that there could be some sort of intersection? Let's take a look. So this is where the triple scalar product is going to be helpful. So if we get a 0, it'll tell us one thing. If we don't get a 0, then it'll tell us something else. So let's take a look. So the triple scalar products, we might have to do that cross product calculation to get the values here and then do a dot product to get a result. We do get a 0. So that, again, that volume between the normal vectors creates a 0. So the normals are coplanar. They're on the same plane. So what does that tell us? There's two possibilities. Either the three planes intersect on a line, or they don't intersect at all. Okay, so what do? Well, we got to go through the algebraic process and try to determine what's going on. So we're going to use an elimination process to help solve that. So now notice this is a little bit different than the elimination process you were looking at before. Here we're going to eliminate x using plane 1 and 3. And then eliminate x using planes 1 and 2. Now what that's going to do is going to give us two equations with x and y. And our eventual goal behind all this algebraic work that we're doing, we're going to use these two new equations to find a solution if it exists. Okay, so this algebra is going to basically tell us if there's some type of solution or not. So again, this work of the triple scalar product and all the parallelism, you could technically jump right into the algebra and work with the algebra to determine what kind of solution you would have. All right. So that is a possibility. It really depends on the amount of work that you can show here. So we're going to take a look at using 4 and 5 to eliminate one of the variables. We wind up getting a very interesting equation that 0z is equal to -12. Now, why is there no solution here? Well, because 0 equals 12, -12 is impossible. Okay, so there's no solution to this system. So if there's no solution, then we have this kind of situation. Plane 1, not parallel to plane 2, and then not parallel to plane 3. So none of these planes are parallel, so they don't intersect in something consistent between all three of them. Okay. All right. So the next example, exactly the same thing. So taking a look at the normals, checking to see if any of the planes are parallel. All right. So in this particular situation, you have planes that are not parallel. So 1 and 2 are parallel, but the third one is not. Okay. So what you need to see is plane 1 coincidental with plane 2? Because it might not be, but it might be. So you check for coincidental, just like we did previously. If they are not coincidental, then plane 1 and plane 2 are distinct. So what we then have is this situation. So is there a unique solution between all three planes? No, there's not. So there's no solution in this particular case. Okay, so another situation there. And a fourth one. So here, again, now here you can just do this by observation. You can clearly see by a scalar multiplication, especially when you have a 0 as one of the values in here. You can clearly see that there's going to be some lack of parallelism. So is this normal scalar multiple of the second one? Absolutely not. Is the first one a scalar multiple of the third one? Absolutely not. Is the second one a scalar multiple of the third one? Well, I need to double this one because this one is a 2 in the first x location. So no, absolutely not. So they're not parallel. So you have this kind of situation. So none of them are parallel, but you check this triple scalar product, all right? And if you get a 0, there's no solution, or it could be a line. And if it's not equal to 0, then it intersects in a point. Now, sometimes questions will tell you, give you the 3 planes and say, these intersect in a point. Okay, they tell you that it either intersects in a line or it intersects in a point. You can avoid, and it's not required for you to go through this process of explaining the normals and what's happening with the normals if you are told what kind of solution you have. You just have to go ahead and find it. So the work that we're looking at here is not necessary if you know for sure that the solution is a line or a point. Okay, it's not necessary. So including this scalar product here. So you don't need this scalar product calculation if you know what type of intersection you have. You just need to go through the algebra and go ahead and find it. So in this case though, if we're not sure, triple scalar product turns out to be 0 or non-zero. That's a 7. So we know that it's a point of intersection, so we have to find it. So how do we do that? Same algebraic process as we looked at before. We're going to pick a variable from the equations to eliminate in both the pairings. So to eliminate y from both of them, you use a system of elimination. You're going to get an equation. Now, the idea behind finding this point of intersection is you want to create an equation with only one variable. All right. So by doing that, you can then find the x, y, and z values. All right. So eliminating y from equations 2 and 3, you get an equation with x. I can substitute that back into the equation for number 1. Now let's take a quick look. You notice the equation for plane 1 doesn't have a y variable. So that's the reason for eliminating y is a good idea, it's a good choice, because it's already been eliminated from equation number 1. So that kind of saves some time. Otherwise, we would have to go through the process of eliminating a variable and then eliminating a variable again to get an equation with one single variable. So from the first equation, we've already eliminated y. We use the second and the third to eliminate the y variable, get an equation with x, substitute that into the other one here. And again, the goal is to get an equation with one variable. So by doing this substitution, we get an equation with one variable, z only. Once we have the z value, we can easily find the x value here. And the x value is given there. So we have the z, we have the x. How do we find the y? Well, that's a pretty straightforward task. You can use either one of these equations to replace the x and the z and find your y. Can't use this one to find y. It doesn't even have the variable y in it. Okay, so you do a little substitution, get that. So again, we have an x value, a y value, and a z value. So x, y, and z. And therefore, we have the point of intersection. All right, so this gives you a sample in terms of the different types of intersection of planes, including the point of intersection and how to deal with some of the algebra. I'm going to be showing a follow-up video using something called matrices if you're curious to take a look at that, but it's not absolutely necessary. It is, matrices sometimes is left for university style questions, so you can take a look at it if you wish. If not, you can use the algebraic techniques that are shown here.